Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. Today I'll be discussing the reciprocal system Macrocosmos database star clusters. That's the layout for star clusters. But first I just want to go back to the galaxy layout, which I did last week, and just show you, if I click into the star clusters underneath the Milky Way here, we can just scroll down, and then you'll see all of them here. So this works perfectly. I'm just going to scroll down and just show you. Let's go to M3, which is the famous globular cluster. Scroll down, scroll down. There it is. Click there, and click the button, and there we are, M3. Now look, you can also get there directly, going here, star clusters from the main menu, and we're back to M3. I don't know that I have, okay, I don't have any stars listed here under it, but if there are named stars within a globular cluster, they would be found here. All right, so let's go through the fields. So we have the star cluster name, of course. In this case, it's M3. And by the way, I have, let's go down here, 198. Let me just go to show off. Yeah, 198 total star clusters. All right, so let's come back up here. Star cluster name, again, that's M3. The new galactic catalog number is 5272. The Messier number is 3. The form number is 1. If there were named stars, they'd be here, and you could actually jump there. Location year, this is the standard J2000.0. The right ascension, 1342, 11.2. The declination is plus 28 degrees, 22 minutes, and 32 seconds. And then here you'd have the general videos, and then for the events you would have anything. I don't think I have anything for here, but these would be like specific happenings relevant to that particular object. Let's just jump to the first one up here. And here's a nice picture from Astronomy Picture of the Day. It shows you the globular cluster M3, so on and so forth. Okay, so then we just come back, hit the button here, star clusters, and we're back. Galactic 1, 2 coordinates here. This time we do have this 42.207, etc. Galactic B, Roman numeral 2 coordinates, 78.708, etc. If there were nebulae and gas and dust clouds within the star cluster, they would be named here. This is a type globular cluster. Now, there are lots of other ones. Well, not lots, but there's a galactic open cluster and there's a constellation of asterism. By the way, you do realize that with constellation or asterism, the stars are not actually necessarily physically nearby each other. It just might be that they're close together in the sky. Okay, so that's my globular cluster there. If there were an abbreviation, it'd be here. So if there's like a, well, let's actually just scroll down here. Let's just see. Let me just let me go show all. Let's go back and let's just take a look. Yeah, here's like Scorpius. Now this is a constellation, and in that case we do have the genitive, which is Scorpii. The abbreviation is SCO, and the translation is Scorpion. Okay. But now I want to go back to M3. So let's go find. Oops, sorry. Let's go find. You type in M3. Click off any field, and there it is. We're back to M3. So I just explained to you these three fields, which will only be used for constellations or asterisms. If you know the, oops, I'm sorry. That's M30. Here it is. M3. When you do a find, just keep in mind it'll give all the M3s, so not just M3 by itself, but maybe M35 or whatever. All right. Here we have the total number of stars, 500,000 for this globular cluster, so you feel that. If you know the gas mass, the gas within the cluster, you put it there. I mean, I have a lot of these fields where we don't have the answer, but I have them here just in case you do, and that's your field of interest. Arc minutes for this is 18. Diameter in parsecs 55.215. Don't have the axis ratio, but it's probably close to 1 because it's globular cluster. Rate of velocity, again, it's really associated not too far away from the Milky Way, so it really wouldn't have a Z. Distance 10.4 kiloparsecs, which amounts to 3.39 times 10 to the 4th light years. Don't have the speed relative to the CMBR. The CMBR is the cosmic microwave background radiation. Now again, the luminosity, I probably don't have many of these filled for this object, but I have this table here for most of the astrophysical objects, so if you know that information, you can plug it in here. And the mass in terms of mass of the Sun, 4.5% of the fifth. In grams, that would be 9e times 10 to the 45th power. And let's see. Gravitational limits of the cluster, 0.742 kiloparsecs for the first gravitational limit. And for the second gravitational limit, again in kiloparsecs, is 2751.9. Total mass and luminosity ratio, well, we don't have that here because I don't have a luminosity. So if you're missing a field, you'll get a question mark. No big deal. Overall metallicity, minus 1.34. And there's an important note here. It says if the concentration of Fe to H is equal to minus 1, then iron has only 1/10 of its solar abundance. So that's what that means. Percent relative to the Sun is 4.57. Okay, parent object is the Milky Way. So this means you can click here and you go back to the Milky Way. So that's fine. Then you'd have to come back, scroll back down to M3 to jump back. Although you could just hit this and it'll jump back. Okay, so either way. All right, so let's just take a look at the note here. Let's see, how big is this? I think it's worth going through. I think this is worth going through just a little bit. Okay, so let's read this note. This is from The Universe of Motion, which is Doobie Larson's magnificent astrophysical work. So M3 contains 274 known variable stars. So from page 30, for instance, Omega Centauri is slightly flattened, and some indication of rotation has been found in the spectra of M3. And then pages 42 to 45, the CM diagram of the globular cluster M3 is shown in figure 3. That's figure 3 of the book. In this diagram, the points representing the magnitudes applicable to the individual stars fall mainly within the crosshatched area. Identification of the locations marked O, A, B, and C has been added to the conventional diagram for purposes of the present discussion. The mass, density, and central temperature of the globular cluster stars are related to the variables of the CM diagram, and although they are subject to modification by other factors so that they cannot be represented accurately in this two-component diagram, they can be located approximately, and adding them to the framework of the diagram for reference purposes facilitates understanding theoretical development. Accurate measurements of magnitudes in the area of the diagram occupied by the globular cluster stars are difficult to obtain. S.J. Inglis points out that, quote, there is no red giant whose mass we know with any degree of certainty, but we can relate these magnitudes to the evolutionary pattern of the stars and thus arrive at approximations of their values. You know, for instance, that the line BC, the main sequence, is the location of gravitational equilibrium. The stars in this line are therefore at approximately the same density. Density to C is actually greater than that at B by a factor of 3 or 4 because of the compression due to the larger stellar mass. But since the equilibrium densities along the main sequence are more than a million times greater than those in the early portions of area O, the difference between B and C is negligible on the scale of the diagram. We may therefore draw lines parallel to BC and treat them as lines of equal density for analytical purposes. Similarly, the line AB theoretically represents a condition of constant mass. The theory further indicates that the central temperatures are determined by the stellar mass. Lines parallel to AB can thus be regarded as lines of equal mass and central temperature. On the basis of the explanation of the line AC that will be developed in the following pages, this line represents a condition in which condensation of a dust cloud of nearly uniform density is proceeding at a rate determined by gravitational forces. We may call it a line of constant growth. Figure 4 is a reproduction of the M3 diagram with lines representing these other variables added. These lines provide a good indication of the way in which the several variables are related to different regions of the diagram, and reference to the pattern of this illustration will be helpful in interpreting the CM diagrams that will be introduced later. The relations represented by the auxiliary lines figure 4 apply to the stars of the globular cluster type only. As we will see later, the corresponding relations, the lines of equal mass, for instance, are altogether different for other classes of stars. This is a fact that has not heretofore been recognized, an oversight that is responsible for many errors in the orthodox interpretations of the CM diagrams. All of the stars of the globular cluster condensed from the same dispersed aggregate of primitive material, but the conditions affecting the ratio of condensation varied, and the evolutionary stages of the stars therefore differ. Consequently, the stars of a cluster such as M3 are spread out over a range of the stellar evolutionary pattern on the CM diagram. The earliest of the visible stars are the coolest, but by reason of the immense area from which they are radiating, their luminosity is relatively high. These stars therefore occupy positions in the upper right of the diagram, in the general area marked O. The remainder of this chapter will give a general description of the paths that these stars follow when they leave the area. Further details will be added in Chapter 8. Again, that's the universe of motion. After some additional groundwork has been laid, the stars, these globular clusters, exist in two size ranges. The great majority are small, in the neighborhood of the solar mass or below. Another portion of the total consists of stars that are substantially larger. We can identify the latter, stars that had a fragment of pre-existing material as a nucleus with the condensation of the pre-stellar dust and gas cloud. The smaller stars are those that did not enjoy this advantage. The fragments incorporated into the stars were usually small, and the explosions that scattered them into space were violent enough to reduce the greater part of the original structure to dust, gas, and small aggregates. The growth of the stellar structure follows. Essentially the same course, whether or not it contains a small fragment as a nucleus. The important difference is that it takes a very long time to build a dust particle up to an aggregate fragment size. A pre-stellar aggregate that has a fragment to start with therefore has a big head start over those that have to build all the way from dust particles and is able to establish gravitational control over a larger volume of the protocluster. Thus, even though the stars of both of these groups are nearly alike at their points of origin in the area O, those of one group have a much greater potential for growth. I think I'm going to stop here. Continues on. Again, I took the liberty of quoting extensively from Larson's The Universe of Motion for the purposes of the database, just so you'd have it handy when you're working with globular clusters or whatever it is you're working with in the database. All right, well, that wraps it up for today. Please study the reciprocal system and prove it for yourself. For the simplest possible treatment, please obtain my work, The Unmysterious Universe. Has all the concepts, many diagrams to facilitate your understanding. Now, if you do want all the mathematics, please obtain my magnum opus, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. 711 pages in the PDF file and 711 slides in the PowerPoint file. Has thousands and thousands of equations, figures, tables, diagrams, everything that you need to have to understand the reciprocal system in great detail. It'll take you months to go through this work. And once you are finished with that, then you should get these two database modules. So let's close out here. Let's go back. The Macrocosmos database module includes the universe as a whole, galaxy clusters and groups, galaxies, star clusters, stars, planets, moons, minor bodies like asteroids and comets, nebulae, gas and dust, and voids. And you can hop over to the events, which comes from the videos or pictures that you put in for each object. Also includes a great graphing package. The Reciprocal System Macrocosmos database has all the properties for matter. Solid matter properties like interatomic distance, valence, specific heat, energy and entropy, thermal expansion, compressibility, electrical and magnetic properties, isotopes and spectra. For the liquid, vapor, gas, matter properties, the program has Lyman density, specific heat, energy and entropy, viscosity and surface tension, electrical and thermal conductivity. And of course it covers cosmic elements and subatomic particles, both material and cosmic. And of course it has photon properties, and like the Macrocosmos, it has a great graphing package. But that's not all. My mentor, Dewey B. Larson, was also a theoretical economist, and I've made his economics work fully computational as well. The package is called Optimal Economist Implementation of Larsonian Econophysics. It covers both microeconomics and macroeconomics. It completely supersedes Keynesian economics, just as the reciprocal system completely supersedes most or all of modern physics. All right, so that's it for today. Again, please study the reciprocal system and prove it for yourself, and thanks for your attention.